Right, guys, can we start? We want to carry on from where we left concerning the sine function. All together? Okay. So what I'm going to do is, I'm going to briefly show you where, but you don't have that graph. So what I'm going to do, let's roughly sketch again the standard sine curve. And then from it, we start doing some variations to get different variations of it. So let's look at this. Okay, let's take this as our reference point, the origin there. Our reference point is there. Eh? Then we've got pi here. Right, for now, I'm not going to be very strict and right and discuss exactly how we got the sine curve. Anybody has forgotten that, you refer to the previous presentation and look at that. So I'm just going to roughly sketch the sine curve and assume that is understood from what we did last week. There is our vertical axis. And the horizontal axis there. Okay, then this roughly say this 4 divisions here, 1, 2, 3, 4. That's 1. And 1, 2, 3, 4 with minus 1 there. I think we saw that at half pi, that function was 1. So we've got a point there on the graph. And it's pi to 0. At 3 halves of pi, it is minus 1 somewhere there. Sorry, this looks like a 2. Let's make it minus 1. There, 1. Then if we continue with that, since the function is periodic, we know that there again is going to be 1, and there is going to be minus 1. Then we draw the graph this way. We get the graph going this way. I think there's a small problem here. Now, this function, if we start here, we're starting at t equal to 0. In this case, t equal to 0 angle in radians. I think if we assume that this started before that, you would know that the graph will continue this way. And so on altogether. I'll leave it like that. So that is sine curve. The amplitude there is 1 and 1. And the period there is t. Now let's just write there period t. In this case, the period capital letter T is equals to 2 pi. And then the amplitude, in this case, is 1 unit. It depends, depending what kind of unit you are using. You could be using millimeters, you could be using centimeters. For a graph like that, I think centimeters will be big enough. Then this one really is just 1 unit. It doesn't matter the unit type of unit you are using. So we've got 1 unit, there's amplitude. So now, this curve will be written as y is equals to sine of t, and this one. Now I want to check a situation whereby now we're going to have y, now the variant of this graph equals to 2 sine t, sorry. We can mark our 2 here again. This is our 1. There was a mistake there, sorry. Then 1, 2, 3, 4. We've got our minus 2 somewhere there. Then here, we've got our 2 there. Please notice one thing. If we've got this angular velocity, let's talk about this angular velocity there. This is 1. There's no difference between this angular velocity and angular velocity there. So which means at this stage, this function and that function, they're all going to travel at the same speed. So at the same time where this one is 0, we expect this one to be 0. Where this one is 1, we expect this one to be 1. The only thing which is going to change is the amplitude, which means now, if we are here at half pi and the function is 1, it's going to multiply by 2. Then this point here is going to be somewhere there. That's for the new graph. All together, guys. Then coming here, exactly the same thing is going to happen. We'll get minus 1 here. Then minus 2 will be somewhere there. Again, at 0, the amplitude is 0, multiplied by 2, it will be still 0, isn't it? Then when we get here, is 1, then multiplied by 2 again, is going to be there. And then, what happens here? Then here again, it's going to be minus 2. If we look at this, remember we used the parabola as our reference kind of to discuss what was happening with when we changed the amplitude. In this case, it was an A, little a. Now the parabola, what was doing? It was closing up, coming closer to the vertical axis, isn't it? Now what happens here? Because at this point here, almost the sine curve is taking almost the route similar to that of parabola. Now let's sketch this curve in such a way that we turn at the turning point there. And let's see where the similar kind of fashion is going to happen with this curve. Let's draw the curve. Now we'll start here. Aim at getting to that point. Come back to the same 0. That multiplied by 2, the amplitude multiplied by 2. Come back to the same 0. Then go up and then down to 0. Then the curve will continue like that to time t equal to infinity. So now I want you to complete this side on your own, but what you can see here, as long as we increase the amplitude here, the graph rises very fast. Look at this point here. If you look at this point just here, the graph was here for the red one amplitude, and they stay, which means the graph grows very faster. And similarly to the parabola, you can see that the graph here comes closer to the vertical axis altogether. So that's the effect of the amplitude. Are we together, guys? Okay. So take note of that and make sure that you can do it. Okay. All right. So now, what we want to do now, what we want to discuss now, let's move on to the next step now. Let's leave the amplitude exactly the same as it is, as standard curve, and change the angular velocity. I love 2, I said it before. I will use 2. Again, they say sine 2t. I think in this case, the position of 2 and the position of 2, they are different. We must monitor what difference does this bring to the graph altogether. Okay. But now, the velocity, the speed of 1 and the speed of 2 are not the same. This must be quicker. What must be quicker? It must be quicker in getting to 0. It must be quicker to getting to turning point. It must be quicker. Everything goes faster now. Is that right? Okay. So now let's look at that. Let's look at that in terms of turning points and so on. I'll leave the graph there as it is. Let's take turning points. Let's take turning points. I'll just write a TP. The standard graph was 0 at 0. This one, I expect it also to behave exactly the same. As long as the argument is 0, it must be also 0. What am I saying? I'm saying the first turning point is at t when the argument is equals to 0. For this function, the argument is not t, it's 2t. So which will mean that 2t equals to 0 altogether. Here I'm putting the situation with the standard graph. Here I'm putting the situation with this graph which I've got here. But this will take us to saying, again, t is equals to 0. Do you agree with me? Okay. Now we'll come this side, the column of the standard graph. The next turning point, the next 0. Oh, sorry, I said turning points here, isn't it? Oh, sorry. Can I say sorry there, please? Sorry. I wanted to say zeros. Such things happens. These are zeros, sorry. Let's start with zeros. So the first zero is there and gives us that, isn't it? So the next zero for the standard graph will be pi. So we expect this function also to, when it sees its argument equals to pi, to also realize a zero. So what does it mean here? Here it means 2t equals to pi. But this means that this should happen at t equals to half pi altogether. So which means then the turning point is going to be there, which you can see it has been done, realized earlier than usual. Then let's get to the next zero. So I'm saying turning point again there. I said turning point. This is zero. So let's take next zero. Next zero will be 2 pi. So we say t is equals to 2 pi. Then I expect this modified graph also to be 0 when it sees its argument equals to 2 pi. By that I'm saying when 2t is equals to 2 pi. And then we know that this will imply that it will mean that t is equals to pi. So then after that, at 2 pi, we know that graph must have realized its full cycle. But now what we were saying here is that this new graph here is going to realize its cycle at half the time, at pi. Is that clear to everybody? Okay. The amplitude is not going to change because it's what? It's 1. Why I didn't change the amplitude? I just wanted to focus on one thing at a time, then we can combine different things, different parameters altogether. So now to sketch that kind of graph, let's choose another color. Is green visible to you? Okay. So now let's do this now. What's going to happen now? The zeros are here, and there, and there. Which means halfway between these 2 points, this function must have amplitude 1. So what are we going to do? We're going to go I hope it's visible, relatively visible. Is that right? So what has happened? The graph actually has been almost like squashed towards the vertical axis altogether. It's, I don't know what to call that. What do you call that? It's been like shrinked altogether. Yeah, it's shrinked towards the x-axis. So what will happen now? It will repeat itself like that, going on to infinity. And at the same time, you must try to imagine what happens as you go to the negative side. Are we together, guys? Okay, so we've seen the effect of that and the effect of that. Are we together? So once we've done that, guys, and once we've done this kind of thing, I think once we've seen the effect of angular velocity and the amplitude, now we can start playing around with things like this. We can take graphs like this. Y equals to 3, maybe sine 4t. Everybody must be able to sketch this kind of a graph. All together? Okay. So now in the our next discussion now, what we want to do is we want to have an operation, well, not a multiplication of t, but we want to operate with t, like t plus something, t minus something, altogether. But we must bring all that experience we discussed with the graph back here. Then from here now, I'm going to really draw rough sketches and imagine that you understand what you want to, try to understand what we're doing there. Altogether. Okay, so let's go to this kind of a situation. Let's say we have y equals to sine t minus pi. See what I'm doing here? I'm just trying to work with the pi, multiples of pi for a start, because I think they're the simplest ones at this stage. So we want to see now what has happened to this thing. The argument is not t, but it's t minus something, or it could be t plus something. So as we're discussing this, we should be parallel thinking about what will happen when we've got sine t plus pi. But we must focus on this fact, we must not overlook the fact that this is the same as t minus All together, guys. Okay. So now let's draw a rough sketch of the graph here. Okay, let's say we've got a pi there, 2 pi, 3 pi, and 4 pi. And this is our t radians, our angles using real numbers in this case, which are radians. That's that. Then we put 0 here. Now, the usual graph will look like as follows. I'm now not going to worry about turning points because I think everybody now has noticed that the turning points happen exactly halfway here and halfway there, isn't it? So now I'm going to just mark 1 here and make sure that I've got a graph which goes there, and there is 1 minus 1, and there is the principal period. I'll just do the principal period only, 1 cycle. Now I want to talk about this function. Listen to me very carefully, guys. If you're going to discuss this function, your reference point will always be the standard graph altogether. Okay? So what I'm going to tell you here, I'm going to say standard, and then the variant. So I'll draw a line there. I'm not expecting you to do exactly like I'm doing. Myself, I'm teaching, I'm explaining. You display your solution the best way you can. But by writing these things, I'm not saying go and write them, but I'm trying to highlight what you must focus attention on so that you don't forget what to do. How to get right? Okay. So now what do we have here? Now, let's start with zeros. Because once you've got zeros, we know that halfway between zeros, there's a turning point. Altogether. So I'm just trying to economize them in terms of time. So let's start with zeros. So we know for the standard graph, the 0 will occur when t is equal to 0. That's the first 0. Now for this function will also realize the 0 when it sees its argument going to 0, or when it sees its argument equal to 0. What does that mean? It means t minus pi equals to 0. Then that will imply that t is equals to pi. So now I'm going to use a different color for this one now. So the first 0 for this variant function, this function will be here. All together, guys. Okay. Then we know the turning. We didn't know the second 0, so let's wait a bit. The next 0 will be t equals to pi, isn't it? So now this one, when it sees its argument now is not t, but it's t minus pi. When it sees it equals to pi, it will also realize a 0. So what does that mean? That means that this will mean t equals to 2 pi. Then the last 0 will be t equals to 2 pi. This function will have its argument. When it sees the argument equals to 2 pi, it will also realize a 0. So that is when this is equal to 2 pi. But that implies that t equals to 3 pi. I hope you see what the use of this thing is, to be able to plot the zeros for the new graph altogether. Okay. Now I've got all of them, 2 pi, 3 pi. Let's plot them. So the other 0 is here, and the next 0 is there. All together, guys. Okay. Now, what's really going to happen? This is what's going to happen. Let me just experiment here. What's really going to happen now? What you see is that the 0 is here. It was shifted to the right. The new graph starts there. All together. I hope you can see the shift. Eh? This is sine t. Then this is sine t minus pi. Everything is delayed by pi. All together, guys. Then now try to imagine now what will happen if we change this also to be 2 altogether. So which means if we're dealing with exactly the same graph, then this graph will be like you see? Altogether, guys. Okay. So that is that. So this is what we call the phase shift. Altogether. There's a phase shift there. That's what we talk about when we talk about phase shift. Right. So now, but the period of the function was not changed. Why? Because there's only one multiplying there. Altogether. So it still has got the same period. It still takes the same time to complete the period. Only when we alter the angular velocity here, then we will see this as a squashing or shrinking towards the curve or widening. Why? When it widen, we go back here. Let's go back here. If here, instead of, where was that? Here, this curve, which was sine 2t. If we had half here, this will occur here. Just check where it's going to occur. It's going to occur at 2 pi, isn't it? Because now here, if you've got half there, what will happen when you multiply both sides, you're going to get 2 pi. So, which means now the graph is going to widen. It's going to take a longer time to complete a cycle. I hope you can sense that. Can you sense that? So now, please now, what we've done now, let's just go back here. We have seen the effect of A as amplitude, and we've seen the effect of omega as angular velocity, and we've seen the effect of that pi there. Let's call it alpha. In other words, in general, I'm going to write this way. To represent this kind of graphs, I'm going to write this thing as y equals to A sine, let's say omega brackets t minus what? Minus, let's say alpha there. Let me just say alpha 0. You say, when normally I say alpha 0 or something, we'll talk about a particular number which we know there. So now we need to understand the effects of all those things there. But what you must notice also here is that if we remove the brackets, obviously it's going to have some shift there. But I think the best thing to see exactly what happens is to leave the graph in that kind of form. Altogether. Okay. Then omega is our angular velocity. What is velocity, by the way? What is velocity? In general, normal everyday life, when we talk about velocity or speed, what are we talking about? We're saying distance over time, isn't it? Okay. So now, what happens here? Omega normally is going to be equal to 2 pi f. But what is f? F is what we call frequency in hertz. This is frequency in hertz, which tells us how many cycles are we doing per second. Altogether. Okay. So now, and this f f is actually equals to 1 over the period. Altogether. Okay. So now it's 1 second over the period. Altogether. Then, which means now that this, if we look at this this way now, this is going to be changed to something like this. A equals to sine 2 pi f multiplied by t minus alpha 0. Altogether. So now, from what we have here, you must be able to read off what is your period. Are we there? Okay. So now, if we've got, let's say with a 3 there, like we did somewhere, let's say with a 3 there, what will be our period? If we've got 3 there, this will be 3, this was just a 3 there, equals to 2 pi f. Now if you play around with this equation, let me just get a new page here. Let's say 3 equals to 2 pi f. We know that 1 over f is equals to our period. Now, if we've got this, we've got 3 there, want to know what is that, we then say this is equals to 2 pi 1 over t. What do you want to know? T, isn't it? What are we going to do? To make t substitute the formula. Then we're going to say multiply both sides by t. We've got 3t equals to 2 pi. Then therefore t is equals to 2 pi over 3. All together. Then you know that this is your period. So now if this is your period, you just take 2 pi and divide it into 3 parts, then you've got your period. All together. Okay. If you are sketching this, I think you know, I don't know, maybe you don't know this, but if you are sketching something like this and you've drawn your graph roughly like this and you've got 2 pi here, put. Now you want the period of this thing. You can just use your geometry, or if you don't know that, it's unfortunate, but I can teach you later if you want to. You can divide this segment into 3 equal parts. All together. Then once you've got 3 equal parts, then you've got 2 pi over 3. You can plot to 2 pi over 3. Then you know that my curve is going to make a cycle from here to, from 0 to this point. All together. Good. So that's that. So I hope now, I don't know what I've forgotten, but we'll still engage with that curve later more precisely. But what we have now, we've got a general sine curve, which is a sine 2 pi over t. I'm just writing that f differently, multiplied by t minus, let's say, alpha 0 there. That's that. Then everybody must understand the effect of all these parameters. Then simplifying that, we can get this as a equals to sine 2 pi over t, 2 pi t over capital letter T minus alpha 0 over t. That's another version of that. So that every time when you've got this, you must be able to, at the end, what's the advantage of this? The advantage of this, it puts you in a position to know exactly how much the curve is shifted to the right or to the left. Then, when you take it this way, then it reveals to you what is the angular velocity. And then when you read this, it will tell you how it is the amplitude. So coordinating all those parameters will give you a precise curve which you want. Otherwise, if you don't, then you're going to get an answer which is upset. All together, guys. Okay. So I think I'm going to stop there. But before I stop there, I want to talk briefly about equations. Let's say trigonometric equations or equations in general. Let's say this. Let's say I've got a function here. In this case, I don't really mind what function I have here. It's just a graph like that. And this function is y is equal to f of x. Could be a different graph, it's a different function, and all those things. Where do we get equations from? Remember, with functions like this, what we are saying here, let's just hold on. When you pick a value on the x-axis like 2, we can calculate y by saying y is equals to f at 2. Then we get the value of the function. What are we doing there? We're getting the value y. Altogether, we've got value x, we value the function, we get the value y. Now, when do you normally get the equations? You get the equations when we have a value y, but we don't precisely know at what point of x do we get that value. Then we've got something like this. Let's say we've got 2. Let's say the value function y is 2. That is equals to f at x. Then now to know where that x is, we'll definitely need the concept of the inverse of that function which is involved in the equation. What do we do then? We introduce the inverse on both sides. Now, if we've got 2 equals to f at x, I was saying that generally, I want people to understand this kind of a situation, that when you've got a function, then I was saying that if you've got a value 2 here, you can find the value y by evaluating that. Then that's not a problem, because you've got the formula for that function. But in the case that you are given a value 2 of the function and you don't know x, by so doing, you immediately generate an equation. So now what I was saying now, it doesn't matter that trigonometric functions, exponential functions, you will then need an inverse of this function in order to know x. You just go back to what we did with inverse. We remember what to discuss with inverse. So if you compose a function and its inverse, what do you do? You get an identity. So now if I'm going to introduce an inverse here and say f second function at 2 is equals to f second function at f at x is equals to x. You see now what happened now? When I do this now, I free x, and now x is assigned this value. This will be the value of what? Of the second function at 2. That will be what x is. So please understand that every equation you deal with, you can't deal with an equation without overlooking the inverse function which concerns that kind of an equation. So you must be able to identify that this is an exponential function. This is a trigonometric function. So now it's the same thing. Now what we've been talking about, we've been talking about sine. And we saw that sine, I don't know whether you saw this thing, but we saw that the domain of this function sine, let's say f is sine, in this case, let me just replace x by t and say sine t. The domain of this function, if you looked at the graph of the function was with values throughout this way, and the values throughout that way. What can you say the domain is? All the real numbers. What about the range? We said now the range are those values which are assigned to the values of t. In this case, you saw that the range, this function was just close here between 1 and 1. So the range is minus 1 to 1. That's that. I'm talking about a number line with a 0 there, but only taking the piece from 1 to minus 1. That is the domain. That's where the graph is going to be restricted in between there. Are we together, guys? Okay. So now, if I'm going to have a situation like this, let's say we've got a situation like this. I've got sine of x, I don't know what is x, is equals to half. Which means here, I'm actually searching for x. There's no way I can solve this equation unless until I've got the knowledge of the function sine second function of x. Now is the inverse of sine. Am I making myself clear there? The inverse of sine. So this takes us to that we need to discuss the inverse of the sine graph. And that discussion also must take us to inverse of cosine, inverse of sine, of tan. Most important, to discuss this thing, you must be, to do the inverse, you must be aware of the range of the function and the domain of the function. All together? Good. Now, let's come to something like this. I've already drawn something here. There it is. Let's have there 1 and the minus 1. That's the rough sketch of the graph, but let's just assume that it's touching the 1 and it's touching that minus 1. All together? Okay. And remember we said the graph of the function and that of its inverse, They are symmetric around what? Y is equal to X. If I reflect it, this thing which is almost on the line here is almost going to go on the line. Then it goes like this. If you look, this part here is reflected there altogether. Then like that. Sorry, like that and so on. Then this side, this part is reflected there. Then like that and like that. All together, guys. So now that is a reflection. That is a reflection of the curve around the line y is equals to x. Do you agree with me? Question. Big, small question. Is this red graph a function? What does it fail? The vertical line test. All together. Sorry, this is a rough sketch, guys. This actually is supposed to come as far as this one here. All together, that pen which was on the top, it comes there. So this touches the lines there, like here. It's supposed to touch there. So it fails the vertical test. Then what we need to do now is not a function, but we need it as a function. We need to convert it as a function. What should we do? We must avoid the repetition. All together. So because a value which is here, it's going to be repeated there, going to be repeated there. So what I'm going to do, this is what I'm going to do. To convert that to a function, the value which is here is going to be repeated there. The value which is there is going to be repeated there. So we must avoid repetition. What we're going to do is, this is what we're going to do. We will delete all these parts which repeat. And delete all the other parts which repeat. Then we're going to be left with a graph which looks more or less like this. Like a kind of an S which is stretched across that thing. And that graph here is what we're going to call y is equal to the inverse second function of x. In other words, now the range of this function, or the domain of this function, is no longer the real numbers, but it must be, the domain must only be -1 to 1. So this kind of an S which we are seeing here will be basically teaching from somewhere -1 here to what? To 1 there. So which basically means that if you are having these values, these equations must be only be equated to values between -1 and 1. So that's why I said before, if you get an equation like sine x is equals to half, then this equation I can solve. Why? Because this value is between -1 and 1. Then I can introduce now sine inverse here, apply to sine, equal to sine second function applied to half. So here I'm going to get x. Here I can either use a table, if I've got a table of values of sine. What am I saying? I'm just asking you for at what angle is the sine function has got a value? Half. Which one is that? That's a special angle. You must know it. 60. So I can say this is 60. But is this the only one? No. Why? Because here you could say 60 degrees. Why? This is not the only one. Why? Because the function sine is periodic. It repeats itself every 2 pi. So now if I want to give the answer in full, I will say this is also x equals to 60 plus 2 k 360 degrees. What am I saying? It repeats every 260 degrees. So every two multiple of 360, it is going to repeat itself altogether. So then I've given the whole set solution. But remember, we said we're going to work out all these things in radians altogether. So if we're going to work in radians, then we're going to convert the 60 to radians, and then this 2 pi to radians. Then this answer thing is going to look like x is equal to what? What is 60 degrees in radians? I gave you the conversion formula that day. Pi over 3. So that's pi over 3 plus 2k pi. Oh, I made a mistake here. Sorry. Well, this 2 is for 2 pi, which is 306, isn't it? Now, here this 2 is a mistake. Please note that. This should be just k, sorry. With a k, because already I've got a 2 there. Unless if I was going to say 2k 180 degrees altogether. Okay. So please note that kind of thing. As you can see, lecturers, teachers, they can also make mistakes altogether. But what is important is you can also make a mistake, but please be mature enough to recognize where you've made a mistake, then you can correct it altogether. Okay, so that's the thing. So now there you're going to have the solution in radians, there you're going to have that. So what is important here is that I've made you experience the graph of this second function, and you saw how we converted it to a function. At that point also, I can ask you to do this exercise. Let's suppose we're given this function. I think we know this function from last week. We talked about this thing. This was equals to y is equal to square root of x. Not really a function, let's just say a relation or a graph. We're given this graph. If you wanted to change it to a function, what would you do? You would say avoid repetition, isn't it? Because functions at the one input, you've got a single input. So now here, we normally talk of what we call principal square root. What is this principal square root, if you know? When we talk of principal square root, what are we focusing on? Only the positive square roots altogether. So now to change this graph to a graph of a function, concentrating on the principal square root, what we need to do is just to delete this negative part. Then this is now a function altogether. With this one and the previous function with sine, there I think I've shown you how, if you've got a graph which you are really interested in it to be a function, how can you modify it, isn't it? Yeah. So in this case, you can expect questions like this, that here's a graph, modify it to a graph of a function. What are you going to do? You must get rid of all the things which repeat and just get a graph which doesn't repeat values anyway. All together, guys? Okay. At that point, I think I'll stop there, hoping that we've understood how different parameters in a sine graph change the graph or modify the graph, and also that we've understood the graph of the inverse sine function. And then when you go to your textbook, please try to read on the inverse cosine function, tangent, and all those things. Then later now what I'm going to do, I'm going to sort of discuss with you the techniques and the ways you've got to engage in order to solve trigonometric equations and any other equations involving other functions. Altogether, thank you for listening.